So again, back to this issue. If I roll a die, so here we are. This is section 4.3. 4.3, which is, what is it titled? Complements and conditional probability. I'm just going to call it conditional probability because that's the main thing. Conditional probability. So I want to give you the big idea of conditional probability. If I roll a die, again, the probability that I'm going to get a 6 is 1 in 6, right? We know that because there's 6 sides, and a 6 is just one of the 6 sides. But now, if you're given the condition, this is where we get the word conditional probability. If I give you a condition, if I look at the die and I say the number is more than 4, if I give you that information, if I say, hey, I rolled a die, and the number came out more than 4, what could the number be?
5 or 6.
It must be 5 or 6 if it's more than 4. So now, what's the probability that it's actually a 6? It's got to be a 5 or a 6 since it's a number more than 4. So what's the chance? 1 out of 2, right? Because probability always has the total on the bottom. Like flipping a coin, right? The chance of heads is 1 out of 2 because that's one of the 2 sides. So notice then that when somebody, if I give you the condition, the information, that the number is more than 4, that changes the probability that I got a 6, doesn't it? That's what this section's all about. Do you realize that's kind of a funny thing? Stop and think, let that sink for a minute. Therefore, probability is actually about knowledge. If I rolled the die and I got the 6, I got the hand tip, and then I didn't tell you I got a number bigger than 4, then you would still think it's 1 out of 6. But if I say, hey, by the way, I got a number bigger than 4, then you go, oh, well now the probability, it's got to be a 5 or a 6, so now the probability is 1 out of 2 that it's a 6. The probability just changed. Why? I didn't re-roll the die. It's the same die. Why did the probability change? My knowledge changed. Probability is all about knowledge. Have you ever thought about that before? That's why insider trading is illegal. What am I talking about? What's insider trading?
Knowledge. What's going on?
Yeah, that's why Martha Stewart went to jail, right? If you're part of a company and you know what they're doing, you're on the board or whatever, you somehow know they're about to split, their stocks are going to go up, then you go invest in them. That's not fair. Everybody else, us on the outside who are not on the board, we don't know. You have a different unfair advantage because you have knowledge. It's not the same risk for you if you were at the board meeting and know they're about to make a move that's going to make their stock go up.
Yeah, the better probability.
Yeah, you have a way better probability. Martha Stewart had an advantage that you and I didn't have. That was not right of her. That's not fair. Right? That's why insider trading, insider stock action is illegal. If you're part of a company and you know what they're doing, you can't trade their stock on the fair market because it ain't fair anymore. You know what's going on. It's like, so probability is about knowledge, isn't it? It's about what you know. Something's only random because we don't know what it's going to do. The future is the future. Whatever's going to happen is going to happen. Every die roll in Las Vegas, every horse race, everything that's going to happen throughout the rest of time in the universe is going to happen. It's only random to us because we don't know, because we lack knowledge. Right? Have you ever thought about that? We're getting a little philosophical here, huh? Getting about that. Yeah, Kevin's getting worked up. I know. It's true, though, right? It's true. Probability is about knowledge. Well, that's what this section's all about. Conditional probability. They're going to give us probability questions, but then they're going to give us a little bit of information. And that's going to change the likelihoods, the chances, the probability. All right. First off, what's the lingo? Here it is. They're going to write, so this first question is kind of it's just the lingo. They're going to go PB/A. What in the world's that? Well, that straight line right there, that big straight line, that is the word given. Well, it's not the word. It's the symbol representing the word given. It means the probability of B given A. So that straight line is the word given. That's just the symbolism they use. All right, so first off, that straight line, they use the word given so often they actually made a symbol for it. That straight up and down line means the word given. So when they write that statement, PB/A, that means probability of B given that A has occurred. That'd be like me saying, what's the probability of getting a 6 given that the number is more than 4? Right? That's what I was doing a second ago with the dice with you, right? I was saying, hey, what's the chance I got a 6? Let me give you some information. The number is more than 4. Well, that makes it a 50-50 chance, doesn't it? Two things, it could be 5 or 6, so it's 50-50. Anyway, so let me get a fresh screen here for this question with all that set up. What are they saying? They're saying A, the subject is telling the truth. A, telling the truth. B is the polygraph test indicated the subject is lying. The poly said they're lying. So A is they're telling the truth. B is the poly said they're lying. The polygraph test said they're lying. So then what does P, probability of B given A, mean in words? That's what they're asking. Well, let's read through it. What does that mean? It means what's the probability of B? What's B? What's the probability that the polygraph said they're lying? So the probability that the polygraph indicated truthfulness? No. The probability that the polygraph indicated lying? Yeah, so far so good. Given what? A, giving they're really telling the truth. That the subject is actually lying? No. Probability that the polygraph indicates truthfulness? No. The probability that the polygraph indicates lying? Yeah. Given that they were actually telling the truth? Yes. There it is. So I just want you to first off know what the symbolism even means. Let's go on to number 2. Number 2. Find the probability that when a couple has 6 children, at least one of them is a girl. We would hope so. So, 6 children, at least one of them is a girl. How do you figure that out? So let me write it here for you. So number 2. Probability at least, not elite, at least one girl in 6 kids. So they're going to have 6 kids. Did I get that right? That was what it said, right? So yeah, 6 children, at least one is a girl. So probability at least one girl in 6 kids. So first off, let's be clear on what does at least one mean? We're going to be using that like 10 problems, maybe 6 problems in a row. At least one. What does that mean?
You mean at least one girl, possibly 6 girls, or anything in between?
Yeah, so at least one means one or more. Right? We good on that first off? Right, if I say I've got at least one coin in my pocket, that means I could have 1 or 2 or 3 or 4, on you go, right? So at least one means one or more, doesn't it? We good with that? They'll be using at least numbers a lot in these next 5, 6 problems. So at least one means at the least there's one. At the lowest there's one, there may be more. That's what that phrase means. So they want to know what's the chance they have at least one girl. Notice, what's the chance they have one girl out of 6, or maybe 2 out of 6, or 3 or 4 or 5, or like Chase said, all 6 out of 6 are girls. That's what they're asking us. What's the probability that they have 1, 2, 3, 4, 5, or 6 girls? At least one girl. How are we going to do that? What would be the opposite of that? What if they don't have at least one girl?
What's the probability? All boys.
That would be all boys, wouldn't it? Are we good with that? If they don't have at least one girl, then they got no girls. They got all boys, don't they? That's how we're going to do probability questions. In fact, I wrote out a little convenient formula to help you. It's on a folder right before class to make it clean. We're going to have like 6 of these in a row. And it's hard for people. These are hard for people to get used to. So I want to write out a definite game plan for you to follow. So here's how we're going to do at least one question. So we're going to give them to us again and again and again. First off, realize or determine the probability of none, right? We already said that's the opposite. The opposite of having at least one girl is having no girls. None. Probability of none. Well, how do you figure out the probability of having no girls?
All boys.
All boys, yeah. So how do you figure out the probability of having all boys? How do you do that? Didn't we talk last time about and or? Am I remembering that right? Right? Let me review that for you real quick. What if I say I'm going to flip a coin and then I'm going to roll a die. And let me put and in between. I'm going to flip a coin, heads or tails, and then I'm going to roll a die, 1 through 6. How many different things can happen?
You get head and a 6, head and 4, and you're fine.
Answer is 12. 2 times 6. Remember, and is multiply. Did you catch that from last time? So it's really important. And is multiply. So if I said, what's the probability of getting, like a heads on the coin and a 6 on the die? Well, what's the chance of getting heads? 1 out of 2. What's the chance of getting a 6? And you multiply those together, 1/12. Do you remember that from last time? And is multiply. I don't remember if I laid that out. Let me. You don't have to write this down, but it's good just to see it, right? You get a head or tail on the flip. Did I write this out last time? Yeah. Okay, and then 1, 2, 3, 4, 5, 6, and 1, 2, 3, 4, 5, 6. Right. So I'm showing you again that there's 12 things that can happen, huh? So you multiply. So and is multiply. All right, let's get back to it then. So what's the chance of getting, in fact, let me do it right here. What's the chance of getting a boy for the first child and a boy for the second child and a boy for the third child and a boy for the fourth child and a boy for the fifth child and a boy for the sixth? That's what we're talking about, right? If they did not have at least one girl, then they had all boys. What's the chance of that? What's the chance they would have all boys? Well, it's just like the flip and the roll. What's the chance of having one boy? 1/2. 1/2. 1/2. 1/2. 1/2. 1/2. What am I going to do? I'm going to add those. I'm going to multiply those, huh? Times. Right? You with me? I don't even care what that answer is. I just want you to get the concept. Is that good? So the chance of having boy is a half times a half times a half. Because and is multiply. Yeah.
How do you get the half from?
Because boy or girl. There's just two things. Just boy or girl. Even, Steven. It's not exactly even, but it's pretty close. They told me to assume it is. So half and half. It's like heads and tails, boy and girl. So then, okay, let's get back to the question. So how do you do the probability of at least one? Well, you start by figuring out the probability of none. What's the probability of none going to be? It's going to be the chance of naught times naught times naught times naught times naught, etc., however many you have. And then, so I'm giving you a general game plan, and then I'll do the particular. And then step 2, then you remember that at least one, like at least one girl, equals one or more girls, right? That's what at least one girl, they're asking me what's the probability of getting at least one girl. That means one or more girls. And that equals the opposite of none. Opposite of none, isn't it? Having one or more is the opposite of having none, isn't it? Okay, so what? Well, how do we always do opposites? If there's a 0.1, let's say 0.2, there's a 0.2 chance of rain tomorrow, what's the chance of the opposite? What's the chance it won't rain? So like if you so 0.2 is 20%, right? If there's a 0.2 chance of rain tomorrow, what's the chance it will not rain? 0.80. You take 1 minus it, huh? Right? If there's a 20% chance of rain tomorrow, there's 80% chance it won't rain. Right? So the opposite, you always subtract from 100%, or if it's decimal, 1.0. Because 1.0 decimal is the same as 100%. Right? We good on that fact? Right? So then if this is the opposite here, so my point is opposites are always found by 1 minus, aren't they? So if this is the opposite of none, then it's 1 minus the none. What's the none? This. We just said it right there. It's 1 minus not, times, etc. There's your formula. So that's what we're going to do in the next 5 or 6 problems. Time after time after time after time. When they say to us, what's the chance of at least one, blah, 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 blah. We'll just go, oh, at least one? That's the opposite of none. So I'll take 1 minus the chance of none. What's the chance of none? You got a not, and not, and not, and not, and not. So you get none. That's what we're going to do. That's the game plan. So let's go back and finish the question now. So number 2, probability of at least one girl. It's 1 minus the chance of not, and not, and not. And we're talking 6 kiddos here, right? I should have written that, 6 kids. So what's the chance of at least one girl in 6 kids? It's 1 minus. Now what's the not? What's the not having a girl chance? 0.5 or 1. I'll just go and go to decimals now. But yeah, 1/2 or 0.5, same thing, right? We'll just go to decimals. So there it is. Let's just crank it out in our calculator. It's 1 minus 0.5 multiplied by itself 6 times. You see why that is? Because each of those 0.5s is a half. It's a chance of not having a girl, meaning having a boy. Boy, 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 boy. Or not girl, not girl, not girl, not girl, not girl, not girl. 6 not girls in a row, 6 boys in a row. So hit the buttons on your calculator. 1 minus. Oh, do you guys know the power button? That'll save you time. You don't have to do it. But the up arrow 6, that'll do 6 of them, save you time. So 1 minus 0.5 to the 6th. I'm getting, whoops, I did 11. Didn't work. But 1 minus 0.5 to the 6th. There we go. I got 0.984375.
Yeah.
Did you get that? I don't know how many decimal places they want. I'm going to go back and see. Whatever, just round it. Let's see, I'll go back, I guess. Do not round. Okay. So there it is, just straight like that. 0.9847. Does that probability seem reasonable? It's always good because you do sense probability. Now, if I said there's a 9, that's 98%, isn't it? Yep. There's a 98% chance if you're going to have 6 kids, you're going to have at least one girl. Yeah, I mean, there'd be a high chance, wouldn't there? It'd be rare to have 6 boys in a row. Wow. And perhaps a little miserable in some ways. It's good to have girls in the mix. All right. We good there? Is that making good sense? All right, because that's what they're going to do again and again. Let's try another one. So there's for in a certain country, the probability of a baby being a girl is 0.464. So the probability is a little bit lower for a girl, just below 0.5, 0.464. Among the next 9 randomly selected births in the country, what is the probability that at least one of them is a boy? So probability at least one boy in the next 9. That's what they're asking me. There's question number 4. So they're saying in this country, it's not 0.5, it's a little below that. 0.464 is the chance of having a girl. What's the probability that you're going to have at least one boy in the next 9 births in that country? So give that a try. So it's 1 minus not times not times not, etc. Because it's the opposite, right? At least one means 1 or more. So it's the opposite of none, isn't it? 1 minus is opposite, and this is a way of saying none. Not a girl, or they're saying boy. They want at least one boy. Okay, so it's going to be 1 minus. Now, what are each of those nots going to be? Not what? Not what? What are we even talking about? Not not a boy. Right? Because they're asking what's the chance of at least one boy. And we're saying not a boy, not a boy, not a boy. Last time they asked what's the chance of at least one girl. So it's whatever they're trying to go for in the problem. In a minute, let's say what's the chance somebody has this disease. So it's whatever they're talking about, we're saying not that. In this case, they're talking about having at least one. They might, now nobody can say, yeah, but they gave me the probability of a girl up here. I know they did. But I'm saying, what question are they asking us? What is their actual question? I don't care what facts they say. I don't care if they tell me how acidic lemons are. I don't care what other facts they give me. I'm saying, what question are they asking me? They're saying, find the probability of at least one boy. That's their question, boy. So when I say not, I mean not a boy, not a boy, not a boy, right? It's not their question. It's not whatever they're asking for. So, so not a boy, not a boy. Now, so I've got to put it here again and again and again, the probability of not a boy. What's the probability of not being a boy?
4.6.
Yeah, the chance of the girl. That means you're not a boy. Although that's been in some dispute recently. But that seems clear in the probability problem, right? They're not a boy, you're a girl, right? So, right, does that make sense? So that is just directly the 464. That makes sense?
Oh, 9, right?
9 of them, exactly. And I don't have room to fit all those in, but you were right.
We usually have 9.
Yeah, 9th power, huh? So I'm going to go dot, dot, dot. But yeah, the easy way is to go 464 to the 9th, or do your up arrow 9. That means 9th power, huh? Like that?
Right.
That good? Let's see what we're getting.
0.999.
We're getting something small, huh? Yeah, 0.999. They want 3 decimal places. Yeah, 0.999. Very, very likely that you're going to get at least one boy in the next 9 births. What's that?
You put it on the little one.
Oh, I did. Because that 5's on the screen, huh? 0.999. There we go. So this answer becomes 0.999. Is that making sense? We good on that? So it's 1 minus not, whatever it is they're asking about. All right, let's try, go on to number 5. It's going to be the same thing, a couple questions in a row here. 5. Subjects for the next presidential election poll are contacted using telephone numbers which the last 4 digits are randomly selected. With the question. Find the probability that for one such phone number, the last 4 digits include at least 1 0. What are they talking about? That's a bunch of fancy talk. Blah, 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 blah. They're saying the last 4 digits. So basically they're saying you've got 4 digits. You know, the last 4 digits of your phone number kind of thing. That could be whatever. 7823 or whatever, right? They're saying what's the probability that you have at least 1 0 in the 4 digits. So it's like having 4 kids, except it's 4 digits. And you're saying, what's the probability of getting at least 1 0 in those 4 digits? At least 1 0.
1 out of 10.
And yeah, so what's the chance? So if a digit is random, yeah, how many digits are there?
There's 10 possible.
There's 10, because 1 through 9 and 0. So there's 10, like there's 6 sides on the dice, or 2 genders, boy, girl. There's 10 possible digits, huh? 1 through 9 and 0. 1 through 9 and 0. So if I was to grab a digit at random, what's the chance it's going to be a 0? Yeah, 1 out of 10. So the probability of a 0 in any one spot is 0.1. That's 1 out of 10. Huh? And what's the probability that it's not a 0? The chance of rain tomorrow is 0.1. What's the chance it's not going to rain? 0.9, right? That's opposite, right? If the chance a digit is 0 is 0.1, the chance it's not a 0 is 0.9. That makes sense because there's 9 other digits out of 10. 9 tenths. 0.9 is 9 tenths, isn't it? See how these fractions and decimals are all telling the same story? They're singing in harmony. Are you hearing them saying the same story? All right, so can you finish up that problem then? So try applying this formula. Do this. It's another at least 1 question, isn't it? So let me let you. So how do you do it? At least it's 1 minus naught times naught times naught times not 4 digits, huh? So 4 knots. Okay, so at least 1 is the opposite of none. So it's 1 minus none, and none is not. So not what? Not what? And this is where people could get confused. I'm trying to make it super clear for you. Not what? Not what they are asking. Not what they are asking for. What are they asking for? A 0. They're asking for a 0. Huh. Like in the last question, they were asking for a boy. And the one before that, a girl. Right? So this really means not a 0. Not a 0, etc. Right? Because that's what they're asking for. At least 1 0. So what's the chance it's not a 0?
0.9.
Right there. 0.9 times 0.9 times 0.9 times 0.9. Or you can just do 4th power, huh? That'd be easier. Just do 1 minus 0.9 to the 4th power. And I'm getting 0.3439.
Yes.
3439. 3 decimal places. So I guess that's 344. 344. Let's see up here, 3 decimal places. 344. Does that came out lower than 50%? Does that seem right? Let's stop it. Let's step back. It's always good with math, all kinds of math, especially probability, because you do have feelings. You sense things. If I told you the chance of rain tomorrow is 99%, you doubt me, and you should. I don't think the chance of rain tomorrow is 99%, right? You have a sense of probability. So does that seem right? But what are we even doing? We're saying, what's the chance the last 4 digits have at least 1 0? Yeah, there's not a real good chance of that, is there? There's a lot of 4-digit numbers that don't have a 0, aren't there? So it makes sense. It seems reasonable, right? I wouldn't expect a 99% answer there. Right? If I say I'm going to pick 4 digits at random, what's the chance? What's the chance that they include at least 1 0? It might be below 50%. Is that good? Is that making sense? Getting the hang of the at least 1? It's 1 minus not, and not what they're asking for. In this case, not 0. Good. They call that complement as well. It means opposite. Complement is opposites. That's where they use that word. The complement is opposite. Here comes number 3. Assuming boys and girls are equally likely, they are, about 50, find the probability of a couple having a baby boy when their 6th child is born, given that the first 5 children were all boys. Assuming boys and girls, find the probability of a couple having a baby boy for their 6th child. Their first 5 were all boys. So their first 5 were all boys. What's the chance that their 6th is going to be
Only 1.
What do you think?
1 or 2.
Not having a girl. Right. Not having any girls.
So it's going to be only 1 chance. Because only boy can have only once, right?
Okay, 1 out of what though? Probability always has a denominator, right?
Yeah. 1 out of 2.
Just 1 out of 2?
Yeah.
Yeah, because the same
Nothing else
probability for
affects
girl.
it no matter what. It's
Good.
the one out of
Good. It's just a half. Yeah. They're trying to trick you. Very good. Yeah, this one does want a fraction, by the way. This one does say. So maybe this is the one you're looking at.
I put 0.5
This
in
one
there
says
now.
fraction.
Yeah,
I put 0.5 in it right
Yeah,
now.
actually,
the other way.
Took it anyway, huh?
Yeah.
All right. Well, that's flexible.
Number 2,
Sounds like they take it either way.
no, number 2 did not take the decimal, take only the fraction.
Okay, I'll check later. So a half on this one, right? We making sense there?
There's only 2. It's either a boy or a girl.
Right.
So
So
6 children are either a boy or a girl.
yeah, it
So
doesn't
50-50.
matter. See how they're trying to trick you with all that backdrop of 5 boys in a row?
Yeah. Adding the extra.
And you hear people talk that way all the time. You'll hear people, like with the lottery, they'll say, hey, these certain numbers haven't been coming up for a while, so you should pick those numbers. No, it's random.
That's why you play blackjack.
Or they could go the other way and say, these numbers haven't been coming up for a while, therefore don't pick them, they're cold. No. There's no such thing as a cold number or a hard. It's all in your heads, and it's all baloney.
Blackjack.
It's completely random. There's no such. Had 5 boys in a row, 3 boys in a row. What's that? 50-50. Right? It doesn't matter. That isn't true. Although we think that way, it's wrong thinking. That's not how probability works.
You have 9 last
That's how
one.
people become addicted to gambling, they tell themselves stuff like that.
Right. Well, we're going to talk all about gambling next week. I got a whole thing to make that clear. Good. So what are they saying? 61% of internet users are more careful. And blah 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 blah. What is the probability? That's what you really care about. When they bring in that word, what is the probability? That among 4 randomly selected internet users, at least one, look familiar, is more careful. So here, let me summarize it. So 61% are careful. I'm probably not among them. And what's the probability? At least 1 out of 4. Isn't that what they're saying? And they say, yeah, selected 4, and they want at least 1. So it's another at least 1 question, isn't it? At least 1 out of 4, I should say, is careful. Isn't that what they want? Didn't they say at least 1 is careful? I believe. Let me go back to it. At least 1 is more careful, yeah. Right, so there's their question, summarizing. That's what they're saying. 61% of people are careful. So if you grab 4 people at random, what's the probability at least 1 out of those 4 will be more careful? It's like saying the chance of having a boy is 61% or a girl or whatever, and you're going to have 4 boys or 4 kids. What's the chance at least 1 is a boy or girl or whatever? Same kind of question. Same formula. Crank it out. Just be clear what the not is. It's always not what they're saying. They're saying careful. So it'd be not careful. So it's always 1 minus not times not times not times not, 4 of them, because it's the opposite of none. At least 1 is the opposite of none. So 1 minus, now, not what? Let's be more specific. I should have written that better. Not careful to the 4th power, huh? Because why? How did it come out? Because they said careful. It's always what they ask about. So if they said at least 1 boy, I would say not a boy. If they said at least 1 girl, I would say not a girl. If they say at least 1 is careful, not careful. Right? So it's not whatever they're asking about. So 1 minus, what's the chance that somebody's not careful? Yeah, if 61% is careful, then not careful is 1 minus the decimal, which is 0.39. 39% of people are not careful. I'm among them. Not careful. So 0.39. It's all us old folks who don't really understand technology. 0.39 to the 4th power. There we go. So whatever that comes out to be, right? 4th power, is it 0.97? I don't know how many decimals they want. 9.7. These want 3? 9.768.
So 977.
They say 3 spots. Yeah, 3 places. So 9.77. Yeah, it was 9.768. So yeah, I rounded it to 9.77. We good there? Now they have a follow-up. Let's go back for their follow-up. How is the result affected by the additional information that survey subjects volunteered to respond? So what if you found out that the people volunteered? Oh, so they're just kind of going back to that stuff we talked about. You know, volunteer samples aren't good because you get people that are highly interested. You don't get the regular opinion, that whole thing. I don't know which one of those says that. See, it is very possible that the result is not valid because the sample may not be represented. Yeah, it's that same thing, right? You get volunteers, then they're not just normal people, right? You're not getting the normal, typical answer. Is that making sense there? All right, so in an experiment, college students were given either 4 quarters or a $1 bill, and they could either keep the money or spend it on gum. The results are summarized in the table. So they're doing an experiment. You get the idea of the experiment? They're giving them $1 to some college students, and they're giving 4 quarters, which is $1,
Right.
to other college students. But the experiment is, do people that have change think of the change differently? Yeah. Value it less. Tend to just think, it's just change, and they'll spend it on gum. Whereas you got bills, you're like, I got money now, right? That's the experiment, right? So we see what happened up here. So students that were given 4 quarters, a little psychological experiment. There were 30 students. Tell me about those 30 students. What do you know about those 30 right there?
4 quarters and putting on gum.
Yeah, 30 students that were given 4 quarters and purchased gum with their 4 quarters. And then what about these 19?
They had to get the dollar bill and spent it.
They were given the dollar bill and they bought gum too. And what about these 35 here?
Dollar bill didn't spend it.
Yeah, they got a dollar bill and they kept it. And then the 13 in the upper right, they were given the quarters and they kept it. So, who kept the money more often?
Bills.
Yeah, the people given the bills did more keeping of the money, and the people given the quarters did more buying gum, right? All right, let's get into the questions then. So, find the probability of randomly selecting a student who spent the money given. That's the most important word in the question. So remember what we said, now we're going to get into the given thing. We're done with the at least one, and we're getting into the conditional, the given that I talked about. They're going to, like when I roll the die and I give you the information that I got a number higher than 4, they're giving us that the student was given 4 quarters. So they're saying to us, if you're going to grab one of these people at random, let me write it out. What's the probability that they spent it given they were given 4 quarters? Remind you again about the dice thing, right? What's the probability if I roll a die just straight out, going to get a 6, 1 out of 6. But if I say, what's the probability that I got a 6? Given, if you're given some insider trading information, if you're given that I got the number is more than 4, meaning it's 5 or 6, right? Then that changes it to what? 1 out of 2. See what changes? The denominator changes because there's less possibilities now. More knowledge means less possibilities. You know more about what actually happened, right? That's what's going to happen on every one of these problems. The denominator is going to get smaller. That's what happens when you're given information. It limits the possibilities. There's not 6 different things that could happen now. They told us, they gave us the information that the number's more than 4, so it's either a 5 or a 6. There's only 2 things that could happen now. That's what's going on in all these problems. Let's go back to this one. So what's the chance that they spent the money given that they were one of the 4 quarter people? So, okay, so you know probability always has the total on the bottom. On the top, we're talking spent. Okay, probability is always a fraction, right? And the bottom is always all the things that are possible. Have the total that are possible. So the total in this case is actually going to be,
The 30 plus the 15.
it's going to be those that were given 4 quarters, right? Because we know they were given 4 quarters. That's what they're saying. Right here when they say these are people, we're talking about people that were handed 4 quarters, not those that were handed a dollar bill. So among that group, so how many is in that group? How many were given quarters?
43.
Yeah, and how are you coming up with that?
30 to 13. Purchased the gum and kept it. Kept the money.
Yeah, oh, right here. Yeah, these guys. Yeah, right on. 30 plus 13. Yeah, those are all the people that were given 4 quarters. Yeah. And how many spent it?
30.
30. Purchased gum. Out of those people.
So 43 and a 30.
Yep. So 30 over 40. And when you put in your calculator, you got to start with the top, right? 30 divided by 43. And they want a decimal? Yeah, they want a decimal to 3 places.
0.698.
0.698. That is what I got to. 0.698. Almost 70%, huh? Almost a 70% chance. So what that's saying, if you grab somebody among the people that were given quarters, 70% of them spent the money. 70% of the people given quarters spent their money on the gum. That's what that's saying. That good? Next question. Part B. Find the probability of randomly selected student who kept the money, given they were handed 4 quarters.
So now you have 13 divided by 40.
Exactly. It just changes the top, right? It's going to be 13 out of 43. Does that make sense there?
0.302.
So this is part A here. Part B I'll do down here. That's they kept it over the 4 quarters. So again, the bottom is 43. There's 43 people that were handed quarters. And how many kept the money? 13. Divide that on your calculator.
There's 0.302.
0.302. What else could we have done to get that answer?
First number, the first answer.
From
1.
1. Right? Because it's the opposite. We could have just taken the last answer, subtract from 1. See how they add up to 100%? Add up to 1.0? We could have done that too. Either way is good. Is that making sense? And then part C asks us kind of the follow-up question. So what do these results suggest? So 70% of the quarter people spent it. 30% of the people given quarters kept it. What does it suggest? A student given 4 quarters is more likely to have kept.
No.
A student given 4 quarters is more likely to have spent the money
That is student giving $1.
than a student given a $1 bill.
No, the one goes.
Would it be?
Oh, no, we don't know anything right now about the $1 bill.
All right, so it'd be a student given 4 quarters more likely
It's
to
just
spend
A.
money.
It's just A. All we know right now. Now, the other part's true, but we don't know that yet, supposedly. It's just A. All this suggests is that a student given 4 quarters is more likely to have spent it than kept it. That's all we know from those numbers. Is that good?
Yep.
All right. I flash off that. Any questions on that before I move along? The actual question is, find the probability spent. So what's the probability that they spent the money given that they had the dollar bill instead of the quarters?
13
Give it a try.
spent.
Probability is always a fraction. What you're given limits the denominator, doesn't it? So the denominator is going to be the number that we're given the $1 bill, and the top is the number that spent it, huh? Right? So whenever you're given information, just like when I gave you the information, I got a number higher than 4. That limits the possibilities. That limits the denominator, doesn't it? So we're given that they were handed the dollar bill. That's what they're telling us. So what's the chance they spent the money given that they were handed the dollar bill? So how many people, let's do the denominator, how many people were handed a dollar bill? 13 and 31. Is that what it is? Yeah, 44. Right? Everybody see that? Because that's all the people, students given the dollar bill. The 13 and the 31. The top, how many people out of that group, how many spent the money? 13. Right? Right here. 13 spent it, purchased the gum. So 13 divided by 44, 3 decimal places, 0.295. All right, then the follow-up question B, find the probability. So that's all A. Then B is going to be the same. Yeah, I'm going to move on. There's harder things. So B is the same thing, opposite, then answer the question. I'm going to move on for good there. Is that making sense? On there? Questions I can answer. So the rest is the same on that. So number 10. So the data represent the results for a test for a certain disease. Assume one individual from a group is randomly selected. Find the probability of getting someone who tests negative given that he or she did not have the disease. So we're talking about medical tests here. No medical tests are perfect. I don't know if you know this, but there is no such thing as a perfect medical test. You can test positive for something and end up not having it, or negative and you do. And doctors, hospitals, they try to manage the false positives and the false negatives the best they can with statistics. I'm planning to show you an example. I've got it all ready. It's just you're not ready for it until you know just a little bit more. Next week, if I have time, I was trying to squeeze schedule. I'm going to show you an example. It's exactly this. It's a given. So really, after today, you'll have what you need. So next week, I'll try to. I'll definitely bring in an example. A famous question. One of the most famous pieces of knowledge that people in society don't know about statistics is. What's the chance if you test positive for cancer that you really have the cancer versus, swap that around, what's the chance if you have cancer that you will test positive for it? Those are actually different questions. And when doctors are asked about those two questions, 95% of doctors get them confused. So it's something that's commonly not understood because of a lack of statistics knowledge, even among medical professionals. So I'll show you that example next week. These are the kind of things I want to make sure you're getting college educated here, coming out the door, that you know really statistics. You can really think correctly statistically about things. All right, so that's all what this is kind of leading to. So the individual, I'll give you the exact example that 95% of doctors messed up next week. So number 10 here. So what are they talking about? Let's make sure we understand that table. We've looked at these kind of tables before. What is that 127? Tell me about those 127 people.
Positive and they do have the disease.
Yeah, they have the disease and they tested positive. They should. They have the disease. Test positive for the disease. What about these 39 people?
Not disease, but tested negative.
Yeah, they have the disease, but the test said they don't.
Right.
That's a problem.
They're not.
Right? Yeah, they'll die. Yeah, that's not good. How about these 7 people up here?
Don't have the disease, but tested positive.
Yeah, they don't have the disease, but this test said they did. That happens. Again, there's no perfect medical test. Our bodies are complex. I mean, doctors do the best they can. Our bodies are super complex. You ever taken any of those biology and anatomy? I couldn't probably pass an anatomy class. There's so much to memorize, and I have a bad memory. It is an amazing system. It makes computers look like child's play. Our bodies are amazing, what they do. And so, yeah, doctors are doing the best they can, but there's different things that get in there and mess up the tests. What's this 127? Yeah, they don't have the disease, and it said they don't have the disease. It tested, so that's good. That's what you want. So, all right. So with that in mind, let's see what we can do here. What is their question? Find the probability of getting someone who tests negative given that he or she doesn't have the disease. That's what you want, right? If they really don't have the disease, you want them to test negative. We're hoping that comes out to be a big probability, like 90% or better, huh? Right? If they really don't have the disease, they should test negative. That's what we're hoping. So let's write that out. The probability of testing negative given, see, it's all about given, isn't it? Given do not have, or I'm just going to write not, no disease. No disease. So the probability of negative given they really don't have the disease. So what does given always do? It limits the denominator, right? I'll bring it down here. So the denominator, this is still number 10 down here. The denominator is going to be limited. So you're going to go negative over no disease. Huh? That's the probability.
So 127 over 134.
Right? They're giving us the fact that we are testing somebody who doesn't have the disease. So you're among those people that don't have the disease. How many people is that?
127 don't have the disease, right?
And?
134 are tested.
Oh, gotcha, yeah. So there's a total that don't have the disease is 7 plus 127, which is, was it 134? So that's the total number of people in this study anyway, who don't have the disease, right? No disease. And among them, how many tested negative?
127.
127.
So
Yeah.
9.1948.
127, so divide those numbers on your calculator. Is that what it is? 0.948. Yep. So it goes up here. 3 places? Yeah, 3. 0.948. Which is good. We want, we're hoping for 90 something, right? If you don't have the disease, you should test negative. Of course, that means if 95 is about 95%. If 95% test negative, that means about 5% test positive, even though they don't have the disease. But
Second opinion time.
yeah, right. That's why their second opinions are because it's complex. The body is super complex. And there's other, these tests are based on chemicals and certain things, and, other things can get in there and confuse that.
Stress play the biggest level in anything.
What's that?
Any kind of thing can really play play the factor inside that.
It's true. It is just true. It's very complex. All right. Good. Okay, want to try number 10? See if you can do number 10 then.
Yeah, I thought we just did 10.
Okay. So, same kind of table. It says, what does it say? Find the probability of selecting a subject with negative. So they're saying, what's the probability of negative given what? Given has the disease. So that's not a good thing, right? This person has the disease, and we want to know what the chance is the test is going to say no. Test is going to say negative when they've actually got the disease. That's not a good thing. So let's figure it out. So probability is always a fraction. The denominator is always everything that's possible, like when I roll a die, it's 6 or whatever. But given limits the possibilities in the denominator, doesn't it? So what are we given? We're talking about people that have the disease. The top is people that test negative. So how many people have the disease? Whatever that is. 315 plus 19. Would you all say that was? 334. And the top, out of that group, how many tested negative?
19.
The 19. So there we go. Divide that on your calculator. And, whoops, I keep doing the wrong button. We get 057. Yeah, rounded to 3 places. 057. So 5.7%. Just over 5%, almost 6% of people who actually have the disease will test negative.
Pretty bad test.
Yeah. But they end up trying to balance that end with the other end, because then they think, oh, we need to make the test more sensitive. It's not sensing everybody that has these. When they make it more sensitive, it becomes oversensitive. It tells a bunch of people who don't have the disease that they do, because it's responding to certain hormone levels or certain other chemicals in your blood, which other things can imitate at times. That's always the problem with medical tests. They do the best they can. They try to balance those. Statistically, they balance those two ends. They want to minimize both false positives and false negatives, and they do their best.
So that really happens when you get false positives?
Yeah, this is reality. Yeah, no. Yeah. False positives, false negatives, both happen. Yeah, that's why people get second opinions and that kind of stuff. Yeah, the body is crazy complex. Nobody understands it perfectly. They're doing the best they can. Yeah, no, sometimes we think doctors know everything, but they don't. I mean, they're doing the best they can. They're very smart, and they're very well educated, but body is crazy complex. What would be unfavorable consequence of this error? What would be the unfavorable consequence of this error?
Somebody could have been diagnosed with it.
Yeah, remember this person tested negative, but they got the disease.
Someone did not receive treatment and could spread it.
They don't get medicine disease.
Yeah, B, the subject would not receive treatment and could spread the disease. Yep, that's the problem, right?
Mm-hmm.
Plus, they could suffer from the disease. All right, shall we move on? Is this making good sense? Getting the hang of given? So the table below displays results from experiments with polygraph instruments. Find the positive predictive value for the test. That is, find the probability that the subject lied, given that the test yields a positive result. So, see what you can do. So let's go through the thing. It says, find the probability lied. So let me write that out. Probability lied, given that the test yields a positive result. What does that mean, positive result?
No, he's lying.
Positive test result.
That means the polygraph deemed them to lie.
Yeah, the polygraph said they lied, right? It went and said they lied. So what's the probability they really did lie when the thing says they lied? That's what they're basically asking us. Because that's what you really want to know, right? That'd be the most important question. Hey, the polygraph said this guy or gal lied. What's the chance they really lied? That's what we're really like. How well does this thing work? That's why they called it the positive predictive value. Like, how reliable is this thing? When it says somebody lied, it's not 100% reliable. What percentage reliable is that? How reliable is this test? See how we need stats to figure that out? So these are the results from their test. What's the probability that somebody really lied when it says they lied, when it gave a positive result? Well, you know, given probabilities always limit the denominator. We're not talking about everybody, but only those that got a positive result, right? That's what we're given. We're talking about somebody that got a positive result. Somebody that the lie detector test said they're lying. That's the denominator. The top is that they actually did lie. So how many people got a positive result out of the machine?
41. Oh,
All those people.
you got all of them?
Right? Because positive test results. Right? Right? Some did lie and some did not. But they all got a positive result out of the machine. The machine said they're lying for all those people, right? So it's one of those people we're talking about, right? Those are all the people that got a positive result out of the machine. And among those people, how many actually did lie?
41.
41. So that's going to be 41. Is that 60? 41 out of 60. So 683, yeah, 3 decimal places. 683. So 68%. That's not that great, is it? So if the machine says you lied, then 68% of the time you did, basically.
This is like if you hypothetically prove that they were actually lying after you took the test, huh?
Yeah, that's the problem, huh? When do we know the actual truth is going? Yeah, right. Yes, the research would be tricky. Is that making sense? You getting the hang of the given thing? So given limits the possibilities, the denominator, doesn't it? All right. Questions before I move on from that one? That there is a 4% rate of disk drive failure. I don't know if that's true or not. Do you ever have your hard disk just in your computer just crash? Everything's online now, huh? We just all store everything online. That's nice. That is nice. Yeah. So if you have a bunch of stuff on a hard drive, which we don't anymore, but if you did, and there's a 4% chance of failure in a year. Question A. If all your computer data is stored on a hard disk drive with a copy stored on a second hard disk drive, what is the probability that during a year you can avoid catastrophe with at least one working drive? Suppose you read that question on the exam in a couple of weeks. Our next exam is a couple of weeks away. Maybe 3, I don't know. Whatever the schedule says. Anyway, how are you going to do that? A lot of the battle on a math test, it'll become increasingly in this class, and I'll try to help you with that, is identification. I'll try to run, in fact, I actually made a YouTube video for identification for the 4th exam and the final. So maybe I'll make one for the 2nd and 3rd as well. Just to simply I'll run through for like 20 minutes on a YouTube, and I'll just say, see these words? It's this type. I won't even solve it the rest of the way. I already did that. I already solved them all on another YouTube. These are already solved on another YouTube. But just the identification is a lot of the battle, isn't it?
Yeah.
You know, on the exam, when they're all mixed up. How are you going to read that? What key words in there can jump off the page and go, oh, it's one of those kind where we do the blah, blah, blah thing. So I want to help you with that. I know that students have told me over the years, that's a lot of the battle, is, if I just knew which formula, I can do them all. I just can't tell when they're all mixed up on the exam. So, kids, so let's start thinking that way. What words in there? This is actually something we've done today.
At least one word.
There it is. It's the at least. You see it right in there? I mean, there's a lot of words up there. But yeah, words like at least one and given need to be gigantic to you because they indicate the problem type. Yeah, there it is right there. At least one. This is an at least one problem. That's what it is. They're saying, what's the probability? What's the probability? At least one drive what? One drive what? What do they want? What do they think? What? Here's the what. Remember, look for the who, what, when, where, why, the question word. What is the probability that during the year you can avoid catastrophe? So if you avoid catastrophe, that means at least one drive works. Right? You got to have a drive that didn't break. Right? If they both break, we're talking about two drives. I don't know if you just caught that second up there. See it right here? So you're putting your data on two hard disk drives, the original and a backup.
One out of two.
And they're saying, what's the chance that at least one drive continues to work throughout the year so you don't lose all your stuff?
96%?
So remember, 4% chance that a disk drive will fail itself, one alone. So how do we do? How do we do at least one?
So one.
What do we do? 1 minus not. Not and not. And what's the not? Not what? Not whatever they're saying in the question. You getting the hang of this at least one? What are they saying in the question? Works. Not work. Not work. Right? Because that's the opposite of one of them working, is both of them not working. See how we're doing that? It's starting to make more and more sense, I'm hoping. Especially after you do the homework. And then we see them on a quiz. And then on a practice exam, by then, it'll make total sense. That's my hope. Keep bringing them to you. That's how it was for me. Math and science was totally confusing first time. Just seemed crazy to me. Then I do the homework, you get a little better. Study for the test, get a little better. Then the final. A lot of times studying for a final, I would have a lot of aha moments in my math and science. I'd be like, oh, I see. It's just the boom. It takes 3 or 4 times. It did for me. Seeing the stuff again and again. Then like, oh, I get it now. So you always just take whatever they're asking about and you put the not and the not for that, right? Because they're saying they want at least one drive to work. Well, the opposite of that is that none of the drives work. So it's 1 minus, and what's the chance a drive will not work? That's the 4%. That's the rate of failure. That's the 0.04, isn't it? Right? Make that a decimal, right? 4%, 0.04. Does that make sense? So that should be it, whatever number comes of that. I'm getting 0.9984. I don't know how many decimals they want. 4, so they'll take it just like that. 0.995. Hey, let me help with something. What if you accidentally did it the other way and you like put 0.96? Like that? If you did that, you know what answer you would get? You would end up getting 0.0786, I think, A4. Anyway, how would you know that can't be the right answer? There can't be an 8%, only an 8% chance you're going to make it through the year. You got 2 disk drives that only have a 4% chance of failing. You're telling me there's only an 8% chance you're going to make it through the year? You know that's not true, huh? Keep your sensibilities about you.
What's the chance it wouldn't work, right?
Well, no, we're calculating the chance that. Oh, what is that?
Yeah. The chance it wouldn't work, 1 minus that number.
No, that's something different. No, that's the opposite of the chance they both fail, which is something different. Yeah. So the chance there that you're going to make it through the year, at least one of them is going to work. Very good chance. And that makes sense. It should be super high, right? because there's only a 4% chance of failure. The only way you're not going to make it through the year is if they both fail. That's pretty rare. Pretty rare. How about part B? With 3 hard disk drives, what would you do for that one? Yeah.
The power of 4 instead of.
Yeah, right. 0.04, 0.04. There's just 3 of them here, right? So third power. You just put third power on that. And I'm getting 0.99, how many, 6? 0.999936, super reliable. Right? Yeah, if you have 3 of them, I mean, it's going to be, what are the odds that all 3 of them are going to fail? Pretty low. And that's what we see. See how probability bears out what we sense? I always like that about probability, that it feels right. That's truth, isn't it? That's why people do backup systems, because it makes it very unlikely that everything's going to fail. We good? Mm-hmm. That? A lot of words there. Testing. There's a lot of words for our math class in here, isn't it? Mm-hmm. Testing for a disease can be made more efficient by combining samples. Did we do a combining samples problem before? No? Okay. Combining samples. This is real life. This is what they do. If the samples from 2 people are combined and the mixture tests negative, then both samples are negative. Get the idea? So to save time, what they do is they'll take something that's rare, and they'll take the blood samples from like 10 people, in this case just 2 people. They'll throw them all in the same petri dish or whatever they're testing in the back room, and they'll test like 10 at once in a mixed up pool. And if it comes out negative, they know all of them were good. All 10 were negative. Nobody has a disease out of those 10. Now, if they pour it in and the mix comes out positive, that means 1 or maybe more than 1 of those are positive. But for things that are rare, that people don't usually have, that are, they just save time because they don't want to do the test for each one individually when it's rare. Does that make sense? This is what they really do. They'll pour them in and they'll test, and if the whole batch is negative, that means everybody's negative. Nobody has the disease out of that group. If any one of them has the disease, then the batch will show up positive. Then they'll have to take the rest of their samples and test individually to find which one it is. But that's rare, and they can save time by just pooling them together. Negative, all 10 are good. Next 10, negative, those 10 are good. They can just crank through quicker that way. Does that make sense? So let's talk about the probabilities about that. That's what they're doing here. So 2 people's samples are combined, and the mixture comes out negative, then both are good. Both are, they're both good, both negative. On the other hand, 1 positive sample will always test positive, no matter how many negative samples it's mixed with, right? So if one in the batch is positive, the whole thing comes out positive. Assuming the probability of a single sample testing positive is 0.05. So let's write that down. The probability of positive is 0.05. 5% chance that somebody's going to have this disease or whatever it is they're testing for. Find the probability of a positive result for 2 samples combined into 1 mixture. And the rest is a follow-up question. Let's just go with that first part. So find the probability for 2 samples. There's not any room to write it here. I'll write it here. The probability of a positive for 2 samples. That's what they're asking, right? Right here. Find the probability of a positive result for 2 samples combined into 1 mixture. So if you take the 2 that each have a 5% chance of being positive, you pour them into the same mixture, and you test it, what's the probability you're going to get a positive result for the mix of 2 samples? Now, is this something we've done already? It actually is, but you might need to think a thought to get there. What has to happen for when you pour them in and the mix to come out positive? So you want the mix to be positive.
All it needs is 1 positive.
All we need is 1. We need at least 1. It's an at least 1 question. Do you realize that? If at least 1 of those 2 is positive, then the whole mix is going to test positive. That's a fancy at least 1 question. You see, they're just coming at us again with at least 1. What they're really saying, the only way you're going to get positive for the whole mix is at least 1 of the 2 is positive. At least 1 is positive out of 2, right? If at least 1 of the 2 is positive, then you pour them in, the thing's going to come out positive. So there it is. Can you crank it out now that you see the type it is? It's just an at least one question. So crank it out. Getting any easier? Is it tricky? 1 minus not, now not what? Not whatever they're saying. Remember, if they say, what's the chance that at least one is a boy? Then we go 1 minus not boy, not boy, not boy. If they say, what's the probability that one of them is lying? Then we go, that at least one of them is lying. Then we go 1 minus not lying, not lying, not lying, not lying, don't we? We just do not whatever they're saying. They're saying, what's the probability at least one is positive? We go 1 minus not positive. Not positive. And then we're only doing 2, right? There's only 2 here. So it's going to be 1 minus not positive multiplied by not positive. And what's the chance of not positive?
0.95.
Yeah, because the chance of positive is 5%. So the chance of not positive is 95%. 1 minus it, huh? So it's 1 minus 0.95 times 0.95, right? 1 minus 0.05 is 0.95. That is not positive, isn't it? So then hit the buttons on the calculator. 1 minus 0.95 to the second power, 0.0975?
Yeah.
0.0975. 3 places. So this comes out 0.0975. Rounded to 3 places, it's 0.98, isn't it? 0.098. That's the probability of getting a positive test result when you dump all these into the mix. And then they ask you a follow-up. I think the follow-up question isn't really clear. I'm not going to put it on the test. I couldn't separate it out, though, so we're stuck with it. So is the probability low enough so that further testing of individual samples is rarely necessary? So they're basically asking, is that a super, super low possibility? No, that's not that low. That's almost 10%, huh? That's 9.8% there. That's not that low. So the event is not low. What do they want me to say here? So the event is not low. So further testing will not be necessary? No, further testing will be. Probability is not low, so further testing will frequently be necessary. There it is. Right? They're making sure you understand what's really happening. They're taking the 2 samples. They're trying to save time. They're dumping them in a big mix. They're testing the mix. Well, 10% of the time, 9.8% of the time, the mix is going to come out positive. Then they're going to have to go back and find out which of those 2 made it positive.
What would be considered too low? Like
I know.
10% or
That's why I think this is a bad question. Because on the next one, the answer is going to come out about 6%, and they're going to go, yeah, that's pretty low. So that's why I would put this on the test, because it's debatable. It's not really clear. And usually they say low is below 5%. But on the next one, you'll see it comes out about 6%, and they're going to go, yeah, that's pretty low. Well, says who? That's just an opinion. Yeah, so we'll just go with it, but it won't be on the test like that. Does that make sense, though, how we got the at least? You getting the hang of the at least one? Right? 1 minus not whatever they're saying. Huh? Whatever they're saying. All right. So, to reduce laboratory costs, water samples from 6 public swimming pools are combined for 1 test for the presence of bacteria. Same kind of thing, right? They're testing pools, they're grabbing a bunch of samples, pouring them into the same bead. It's exactly the same. So, blah, 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 based on past results, 0.01 probability of finding bacteria in a public pool. So the probability of bacteria is 0.01. So find the probability that a combined sample from 6 pools will reveal bacteria. So they're going to take samples from 6 pools, dump them all in the same mix, and then test the mix. And they're saying, what's the probability that we'll see bacteria in the final mix? You're going to see bacteria in the final mix if there was bacteria in at least one. It's an at least one question, huh? So that's the same thing. There'll be bacteria in the final mix if there was bacteria in at least one of the samples. So it's another at least one. Probability, at least one bacteria. Can you crank it out now with the greatest of ease? Let's do one more of these. This will be our last at least one. One minus not, all multiplied together. Okay, so it's 1 minus not what? How do you know not? Not what? Not whatever they're saying. Yeah, not bacteria, huh? 1 minus not bacteria to the 6th power, because we're talking about 6 samples, huh? Is that good? It's always not whatever they're saying. So it's 1 minus. Now, what's the chance of not having bacteria? The chance of bacteria is 0.01. So what's the chance of not bacteria? 0.99, right? If there's a 1% chance of rain, 99% chance it won't rain. Right? Not bacteria is 1 minus 0.01. It's 0.99. So this will be 0.99 to the 6th power. So it's 1 minus 0.99 to the 6th power. 0.0585. But then we got to round it to 3. So the final answer is 0.059. Yeah, now here they're going to go, hey, is that high or low? Remember, back over here, they said 10% was high, 9.8% was high. They're going to say, hey, that's quite low. Indicating that testing of individual samples will be a rare necessity. Yeah, so that's just their opinion. I mean, they're calling 6% low, and they call 10% high. Whatever. I'm not going to put that in the test like that. It's debatable. But there's the answer they want. Is that making sense on the at least one? We good? Can I flash off that? Right there. There's our answer. All right. Okay. At least one is equivalent to what? One or more. Good. There, at least one means one or more, doesn't it? The complement, what does complement mean? Opposite. The opposite of at least one, the complement, that's funny looking. The opposite or complement. It's weird that complement's opposite, huh? I always think about it saying, you're such a great probability. It's not that kind of compliment.
Like, oh, that complements your personality.
Yeah, right. But actually used that way, it does mean that. If something like if your spouse compliments you, meaning they're strong where you're weak. They are opposite in some way, filling you in. Like they, anyway. So it does mean that. That is what people are meaning. So the opposite of at least one. Yes, is the opposite of at least one is none. Right? Because at least one is one or more, so the opposite is none. Good on that? 18. A blank probability of an event is a probability obtained with knowledge that some other event has already occurred. Yeah, that's conditional. That's the given thing. Right? That's like when I rolled the die and I said, hey, I got a number bigger than 4. That's conditional probability. What's the chance I got a 6 given the condition that I got a number greater than 4? And number 19, fill in the blank. Confusion of the inverse. Oh, I didn't use that word. Yeah, let me tell you that. Confusion of the inverse. That's what I'm going to bring next week. I'm excited about next week. I've been preparing for it for a long time. I want to show you the medical example. That is confusion of the inverse. That's what it's formally called, that 95% of doctors confuse. That is, it's this one right here. They confuse the probability of B given A, and they think it's the same as A given B. It's really not the same. But it's easy to think of it as the same thing, even for medical professionals. It's not the same. A given B, B given A. That's called confusion of the inverse. They think you can invert them and it's the same. It's not the same. Specifically, the chance of cancer given a positive result versus the chance of a positive result giving cancer. They confuse those, and it's not the same. And that's important on that.